You have fallen into Event Horizon with John Michael Gaudier. In today's episode, John is joined by Puzia and Rohan Rahatgaonkar. Puzia is a professor of astrophysics at the Institute of Astrophysics of the Pontificia Universidad Católica de Chile, where he and his team study how galaxies, star clusters, and stellar populations form and evolve across cosmic time. By combining wide-field multi-wavelength imaging surveys, precision spectroscopy, and state-of-the-art data analysis algorithms on high-performance computing platforms, his research traces the chemical enrichment of galaxies, stars, and planetary systems throughout the universe. Most recently, he and his team are coordinating an international observing campaign on interstellar comet 3I Atlas, the third known visitor from another star system, using ESO's Very Large Telescope, ALMA, Gemini South, and other facilities. He is also the creator of the Golden Webinars in Astrophysics YouTube series, which have brought Nobel laureates and frontier astrophysics research to a global online audience. Rohan Rahatgaonkar is a third-year PhD student at the Institute of Astrophysics at the Pontificia Universidad Católica de Chile. He studies galaxy formation and evolution using deep, wide-field surveys of nearby galaxy groups, building a comprehensive census of galaxies out to 18 megaparsecs, which is about 58 million light-years. He completed an MS in astronomy at San Diego State University and earned a BS in physics and mathematics from the University of Toledo.
Doctors Thomas, Puzia, and Rohan Rahatgaonkar, welcome to the program.
Pleasure to be here.
Thank you.
Now, gentlemen, you have been studying the enigmatic object, 3I Atlas. And 3I Atlas it's a comet, of course. However, it's an interesting one because it appears, based on sort of what we can constrain, it appears to be 7 billion years old and from another star system. And it has a very odd ratio of nickel to iron emissions. We're seeing chemistry involving nickel very strongly with this object. Has that changed? Are we still seeing the nickel right now as because it just passed perihelion a couple of weeks ago? And has that changed? And what does that tell us? What does that nickel ratio tell us about the composition of where this thing formed?
Yeah, those are all very good questions. So let's take this step by step. When the comet was discovered at roughly 4 astronomical units and a little bit beyond, it was basically coming in a cryogenic state as it was sort of preserved in the interstellar medium and the, potentially a little bit of an intergalactic medium above and below the Milky Way disk. And it thawed for the first time as it approached the sun. And so compounds that are easy to break apart, that are easy to float at the surface and be basically photolyzed by the radiation of the sun, were showing emission lines, right? And so nickel was coming out first, as it's basically first available at those distances. This has been observed before, so 3I Atlas is not really exotic in that sense. And a little bit later, as the comet approached the sun more and more, iron actually kicked in as well. And so now we are observing a nickel to iron ratio, which pretty much approaches typical nickel iron ratios of solar system bodies and also 2I Borisov values. So there is nothing really surprising in that sense with regards to the ratio of these elements. The onset, though, and the intensity of both as the comet approached the sun coming in pre-perihelion was a little surprising. And so the chemistry that needs to be basically in place as interstellar objects drive through the heliosphere and towards the sun. It needs to be preserved in a very delicate equilibrium, right? So it needs to be very cold, it needs to be sort of pre-processed in a way that these parental elements and molecules are there in the first place. So we think there is a parental carbonyl channel that is at work. And it was actually beautifully confirmed in the second paper that we published. When we detected the iron emissions, all checks out, all is really perfectly consistent with the chemistry that we are expecting as the comet heats up, not only at the surface, but also at the subsurface layers. And so the presence of carbonyl, nickel and iron carbonyls, is sort of consistent with what you would expect from this cryogenic environment the comet spent billions of years in, as it had traveled in between the stars in the Milky Way and was bombarded by cosmic rays, right? Or actually had some radiolytic activity inside its mass, its nucleus, and was sort of cooking very, very slowly and gently these carbonyl molecules from CO pretty much, and some residual heavy nickel iron, let's say, elements, compounds that are available, probably from somewhere really exotic. So the formation history of this object, given its current chemistry, is really interesting, right? So it means that this thing probably spent or was formed in the outskirts beyond the CO2 ice line, probably a little bit beyond, and or was put there coming from the interior solar system or the exosolar system, as it also contains obviously some form of iron and nickel elements, and probably also silicates and other compounds that we still have to analyze. But this is a very, let's say, hybrid type of object that has a lot of icy material. So it speaks to basically a formation or the preserving of the material that comes from the outer protoplanetary disk. However, it contains also some heavier elements, which means that it's a mix of sort of the interior and the exterior planetary disk material.
It's a fossil. In other words, it forming outside the ice line in its original star system, wherever that may be, then getting into cryogenic deep freeze in the interstellar medium immediately makes this different from a solar system comet out in the Oort cloud. This is different material. But contrast that with 2I Borisov. And what are the differences between this object, this interstellar comet, and Borisov as far as a chemical nature?
So for comparison, speaking strictly about 3I in terms of nickel and iron ratio, there and some other studies. So for example, there's evolution of 3I Atlas. Before 3I Atlas, relatively, there have been studies by Manfroid et al., which studied like 20 solar system comets, which found also nickel to iron ratio with heliocentric distances, but these were not a time series. They were just instances of like you take one shot exposure and you find the nickel to iron ratio. And as Thomas said, the evolution demonstrates that initially, as 3I was farther away, it was exotic because of the carbonyl change, where the nickel and iron atoms are sublimating, which are the carbonyls, and the nickel and iron ratio should depend on the temperature and thus heliocentric distance, which means as the comet is getting closer, you should see increase in these sublimations. And if we compare this to, I would say, Borisov, we also saw a nickel to iron ratio in Borisov, but this was after basically post-perihelion. And I would say the significant thing that you can see is we would need to study a 3I Atlas post-perihelion to have a fair comparison with how the production rate varies with Borisov. So because it's post-perihelion, Borisov is going away, you see a reduction in the nickel to iron ratio. This can be clearly seen in the comparison plot that we have in our paper.
Now, what of a solar system comet? I mean, the differences between this and, say, I don't know, Comet Inky or something like that, just picking any random solar system comet, are you seeing surprising differences between 3i Atlas and what we see from our star system, where the comets might have been a little bit warmer over their history because they haven't been kicked out into the interstellar medium? What is the difference in comparison?
From the total nickel iron content, 3i is actually relatively enriched. So at the current, so the pre-perihelion current sampling heliocentric distances, that compares to really extreme iron nickel production rates that we saw in like really exotic comets in the solar system only, that really travel very far out and spend basically most of the time in these icy conditions and then come in, for a visit every few 100,000 years maybe. The Jupiter family comets typically have, where they were sampled, much lower, like typically 2 orders of magnitude lower production rates of combined iron and nickel. So in that sense, this is an extreme object that had these parental molecules, readily available and had enough accumulated over its journey throughout the Milky Way galaxy. So there's a significant time component to this, where the reservoir of the ingredients that make this iron and nickel emission have been accumulated over much longer timescales in much cooler environments probably than we have, in the solar system and in the Oort cloud and Jupiter family comets. So, but I want to stress really that this is not a very, very exotic thing. It's within the range of what we actually expect. It's just that this interstellar object comes in unprocessed, right? So there is a completely different volume of the parental reservoir of these elements that produce this iron and nickel emission.
So, for example, to give a sort of differences and similarities comparison, what I could say, what makes 3i normal? For example, there's metal emissions which are present, there's metal and nickel and iron which is detected like other comets, so it's not an exotic metal that has been discovered for the first time. There is stabilization of nickel to iron ratio, so after the initial extreme values, the ratio converged to about 4:1 in late September, which is sort of similar to what we observe in solar system comets. So after it got sublimated as it came closer. In terms of carbon chain depletion, for example, CO2 to H2O ratio, 3i shows a 7.6, which is much higher than Borisov, which showed a more typical value closer to solar system comets. But the carbon chain depletion model, if it is something that was first talked about by Ahern paper in 1995, and they have these different production rate ratios, and these ratios are similar to the Jupiter family comets from the Kuiper belt that we observed. And there is also correlation, for example, for nickel to iron to C2 to Cn, which once it stabilizes, 3i falls and on the correlation line between the metal ratios and carbon content that defines the other cometary taxonomy that we see in their solar system. And in terms of differences, extreme differences, that would be the JWST result of CO2 to H2O, which showed more typical values closer to solar system, but much higher than Borisov, and which suggests either fundamentally different formation environments or different degrees of processing that can happen. There is also the metal abundances. So as our initial paper saw, there was metal production rates were much higher, and then they decrease. So it's the time series of processes that differs. I wouldn't say actually the content or the actual material that is not the exotic part. It's how they sublimate, when they activate, when the comet starts to outgas, and basically how it reacts to the radiation from our solar system is what the interesting and different part is.
That's right. So if I may add something to this a little bit, I think there is a phase shift in the astronomical community going on right now with respect to actually how to understand comets, right? So comets, they're all like in their own right interesting and weird and unique in a way, but the real understanding actually comes from the monitoring of these objects. And so I think we arrived at this inflection point in history where the Rubin Observatory will just throw at us one plus of these types of objects per year that we have to follow up, right? We have to follow up spectroscopically with, detailed imaging, even with isotopic ratio studies, maybe with different wavelengths from radio to really UV and beyond, maybe. And so that requires resources. And so we feel this already with 3i Atlas. We're basically saturating the observatories right now because we're asking for so much observing time. Luckily, we're getting this. But I think if we extrapolate this to 20i, 25i, the observatories will say at some point, well, thank you very much. What's so unique about this next object? So unfortunately, the availability of these resources to monitor them and to really track them throughout their journey in the solar system gives you a completely different picture of their chemistry, their dynamics, and basically tells you a lot more about their origins and about their journeys through the Milky Way. And so I think in the not hopefully that distant future, we really need dedicated telescopes that can, with dedicated instruments that can follow these objects as they track basically through the solar system.
Yeah. How about dedicated spacecraft that are sitting out in space, ready to go and look at, interstellar objects as we see them? Because I think you gentlemen are going to be very busy because of Vera Rubin from now on in characterizing it. But this literally is a sample return mission from other star systems. And of course, you can't really tell what star system they originated from, but you can get a profile of what other star systems are like. So what about the weird stuff? Is there anything in this that just indicates to you that, yeah, this is not from here? This is so far outside of what we would expect from a solar system comet that we can start speculating about the formation of the object and perhaps even what kind of star it formed around. Are we getting into that territory yet?
I would say give us a few months longer because we really need to sample the more interior layers post-perihelion as they really get heated up and gas out, and we get an opportunity to really get detailed spectroscopy and isotopic ratios basically of this object. We will be able to probably nail this down a little bit better in its origin, location, and epoch of the evolution of the Milky Way, and probably say also a little bit more about its journey through the thick disk as indicated by its trajectory. Saying anything that I think makes it absolutely unique, exotic, is at this point unwarranted. I mean, we have some really unusual values in nickel over iron, also in CO2 over water, but this is a snapshot at the moment, okay? So this is really important to understand. These objects are actively, really dynamically, thermodynamically, chemodynamically evolving as they are moving through the solar system. And so from one, Polaroid picture of this, you will have a hard time really inferring its origins and where it came from. I think it would be really interesting to me if, in post-perihelion spectroscopy, there would be some other really interesting elements showing up, like, who knows, phosphorus, for instance, right? So that would indicate immediately some interesting nucleosynthetic enrichment and probably potential for, seeding of life somewhere else in the Milky Way galaxy. But I want to really hedge my bets here, and we are letting the data speak. So we don't infer anything, we don't expect anything. We take the spectra, we reduce the spectra, we look at the spectra, and then we let the cards basically fall on the table and then let the universe speak. So I think the less noise you make, the clearly the universe will speak to you. That's a general, I think, insight from my career.
If I could add. Yeah, so maybe one thing that, although as Thomas says, we don't have an idea of where it exactly came from, but we can maybe talk about first why we think it's interstellar and what sort of environments it might have gone through that are possibly there in the interstellar environment. And giving an idea of its journey is something I think is interesting and maybe something that might help you understand when in future we reduce the phase space of exactly what environment. So first, one of the things of why we know it's interstellar is a comet. Three things. It could be its size. So there have been three objects, Oumuamua and Borisov. 3I Atlas is much bigger. The HST observations put the diameter at 5.6 compared to Oumuamua. It's hard for me to say that word, which was 400 meters, I think about, and Borisov, which was about kilometer. Another thing that tells astronomer is its speed. It's traveling at about double the velocity of other two comets and the direction that it's coming from. So Oumuamua and Borisov came from above us in the same general direction as our solar system is moving through the galaxy, while 3I is sort of T-bone. It's coming from the inside, aligned about 3 or 5 degrees with our ecliptic, which is a coincidence. So this sort of tells us that it's an interstellar object that is coming. And one of the things, or during its 7 billion years, I think is its age, 3I Atlas could have traveled through many variety of galactic environments. So some of the environments that we can think about are, for example, a giant molecular cloud. These are the coldest, densest regions of interstellar medium. And molecular clouds is where stars form, and they contain abundant of CO, H2, and complex organic molecules. And so an interstellar comet passing through the molecular cloud would be exposed to these cold, molecule-rich environments. It could have been going through a star-forming region. These are molecular clouds undergoing active star formation with protostars and outflow. So regions which contain UV radiation from young massive stars, enhance cosmic ray fluxes, and possible supernova shocks. And so dust grains and ices can be processed in these energetic environments. And so 3I may have passed through or been near such regions multiple times during its 7 billion year journey. It could also be explained through the supernova environments themselves. 3I might have passed within several tens of parsecs of a supernova. It would be exposed to intense shocks, high energy radiation, and elevated cosmic ray fluxes. And supernovae also eject metal enriched. These could be the source of the metal vapors if they basically rain down on the comet's surface as it's passing through. It also passes through diffuse interstellar medium. Most of the journey was likely spent in this region of ISM, which have ionized region, which have neutral regions. This is where the steady galactic cosmic rays, irradiation, can accumulate over billions of years. And these cosmic ray fluxes basically is relatively uniform, and it basically gives a constant dose to very high levels over like giga-year timescale. And as it was crossing the galactic disk, the thick disk, which is about 1,000 parsecs in scale height, so 3I likely crossed the denser galactic midplane multiple times during its journey, and each crossing probably exposed it to higher densities and potentially different radiation environments. So this shows you that the interesting part of this comet is not only that it's an interstellar object, but it's sort of an invitation for astronomers to go from surface theoretical lab chemistry of actually seeing when nickel and carbonyl atoms in lab like sublimate, all the way to star formation, to extragalactic astrophysics, to supernovae, to exoplanet, to protostellar evolution, galactic disks. So it's an amalgamation of all different fields of astronomy coming together. Sort of, I was telling Thomas, sort of like a hackathon of astronomers. There's this object, bring all your expertise from different aspects to try to study this. Maybe that sort of gives you an idea of the phase space of where astronomers are thinking it could be coming from.
Now, gentlemen, let me ask you this. It seems to me that all right, this could get a lot stranger if you had a future interstellar object that has been through multiple different environments across its history, or worse, been near a supernova. You might see something, and as Vera Rubin telescope unveils this, this could get a whole lot stranger than this. And much has been made about this object being strange and potentially of alien origin. I do not think that's what this is, but would you like to address that and tell us also How much weirder can this get as we study natural objects from the rest of the galaxy as this moves forward?
Yeah, sure. Let's think about how stars, in really large fractions form in galaxies, in the Milky Way, in galaxies in general. They formed in a clustered fashion. So that means that many stars, right, are experiencing the aggregate star formation mechanisms of their neighbors. And so that means that there is a environmental component to the birthplaces, how they, enrich each other, how they truncate their protoplanetary disk growth and evolution of the planetary systems, and how they dynamically later on interact, right? And all of this, like Rohan beautifully explained, is this amalgamate of mechanisms and processes that basically drives the chemistry, the setup of the chemistry that is then released into interstellar, potentially intergalactic space. And then we have the chance and the luck to study these little time capsules, this chemical time capsules locally. How strange this can get, be my guest to go crazy with, nucleosynthetic enrichment locally. If you look at supernova remnants, that stuff mixes on timescales of probably, several tens to hundreds of millions of years perfectly back into the ISM. But before that, and especially if you're coming from a star cluster, an open star cluster where you have been formed around, a normal star, the chemical variance that can really skyrocket, right? In many different aspects of these pockets of the periodic table islands of element overdensities. And so we might run into, I don't know, a weird alpha element depleted object or alpha element enriched object. So we need more data, right? We need more data about many, many more interstellar types of gas components, dust components. And ideally, like as you hinted at already, I think it would be really the time to think about, a steady state constellation that we park in some energetically favorable orbits in the solar system, and then intercept not only one, but intercept many land probes and have sample return missions. These days, launch costs go down, an order of magnitude per decade almost. So I think this is getting really into the feasible territory, and I think it would be a step forward in our understanding of the nucleosynthetic history and the chemistry, the potential chemistry of life in the Milky Way.
Now, speaking of life, comets are linked, of course, to the abiogenesis, chemically speaking. They deliver the building blocks, or at least they have them. What are we seeing on that front? I know we obviously see carbon, but is this looking like, is there anything else, in other words, that might look like the chemical building blocks of biology from this object?
As far as we can tell at the moment, this object looks like it's carbon depleted, right? So there is a lot of CO2, a lot of simple compounds, and what we have at least detected so far in the surface reflectivity and the characteristics of the emission lines versus troughs, absorption troughs of molecules versus individual atomic emission, hints that there is actually not that much complexity in this object, which is kind of surprising because you would expect that the processing, and I'm not a chemist, we're not really chemists, but I think it's easy to see that if you go further and further out in the solar system, the accumulated goo on the surface of these trans-Neptunian objects becomes actually really substantial. And so scanning that, getting samples of that, investigating this in a lab environment on Earth, I think would be really interesting. There is limited diagnostic capability that we have at the moment, since we are basically photon limited at the moment to say much more about the exact polycyclic aromatic hydrocarbons that might have been accumulated on the surface and other compounds that might be lingering there. So it is tricky because this object is not very bright. And so we are, even with 8-10 meter class telescopes, even with James Webb, there is a limited amount of spectral resolution and diagnostic power that you can accumulate to investigate the surface chemistry. I think with a sample return mission, that would be a completely a quantum leap in our understanding of these surface chemistries of these interstellar objects. And I think that should be the necessary step forward.
When is the next opportunity to look at this with Hubble and Webb? I know that some, especially amateurs, are already observing after perihelion. However, you have these giant zones of avoidance with these really expensive telescopes, and you can't point that thing anywhere close to the sun. When can we expect observations from those? And how about the Mars probes doing observations? Or when are we going to see that? I know the government shutdown up here has created a lot of problems regarding that, but when are we going to know more from those types of spacecraft, NASA and ESA, and also Webb and Hubble?
Yeah, so Webb, I think, is scheduled
for December 14, doing its closest approach to Earth. I think December 8th.
19th, I think.
19th? Yeah. So right now it's in post-perihelion. So we, for example, would start our observations of the comet using the telescopes we have from November. I think it gets close on November 18th. But given now from the southern hemisphere, we can observe it during the dawn time. So just a couple of minutes to hours before sunrise. And so our observations would start late November, like 26th. And as the time goes on to December, we can see it for longer periods of time. So I think you would start seeing more observations and then follow-up results of how the comet it survived and how the outgassing is during the November-December period. And JWST, I think, is scheduled for December observations.
James Webb, of course, cannot pivot because of its sun shield, right? So there is limited observability in the scheduling. So in that sense, it was probably the worst trajectory that this comet could have taken behind the sun, and so we really can see this only on the way in and basically on the way out. Hubble has, I think, also scheduled observations next month, if I'm not mistaken, and unfortunately, that facility is challenged by the single gyro tracking mode. So we can only take very limited exposure times, tracking basically this relatively fast moving target on the sky with Hubble. But people have successfully observed with both facilities, and I think that will be repeated, and more instruments will chime in and provide us with much more diagnostic power and data insights. As for the shutdown, I think, this is an unfortunate state of affairs, but it ended luckily. And I think there is, absolutely no malice behind this. We know that reducing and analyzing data is really challenging, especially if you're observing something that your instrument is not really made for. And so everyone is expecting the high-rise images to come through, and I think they will be amazing, and you will see probably a very nice, unique perspective on the side view of this object with its tail. But don't get your hopes super high, because the angular resolution is basically going to be similar to the HST imaging. I mean, it's going to be a little bit better, but it's a half a meter mirror, so there are limitations, physical limitations to what we will be able to see. So, but in any case, it's very, very good to have different angles of evidence. It's very good to have different perspectives, and I think every data set and every data piece is really important for our building this symphony of understanding that we have about this object.
Yeah, and one of the unfortunate things about the shutdown up here is that you get locked out of the building.
That's right.
During a shutdown. You're legally not allowed to go into the building, so the scientists are sitting there at home.
Yeah, of course.
They can't really do much of anything.
I mean, I feel for them, right? It's that you probably, you want to publish. They probably have on their hard drives at home the images and are looking at them and, are basically marveling at the probably the tail, the dust tail, and the coma, and they cannot release it to the public. But a little bit more patience, and we will be surely have a positive surprise.
Yeah, give it 2 weeks. Give it 2 weeks. I think
Yes.
anyway.
Yes. Yeah.
Now, when studying these objects and gaining basically a sampling of the Milky Way galaxy, which is certainly something that we didn't foresee, 20 years ago, we didn't think we'd have this, but now essentially we don't really need to start sending out probes to other star systems because the other star systems are sending natural samples to us. Do you think over time we can get, say, we know of 100 objects, as you were saying earlier, and we have characterizations of them? Do you think that's going to give us basically the geology of the Milky Way? In other words, will when you get a large enough sample that tell you in and of itself basically what the rocks of the Milky Way look like, or at least the comets?
Absolutely. I think this is going to be the next really quantum leap forward in understanding how elements are recycled, and built into planetary systems and eventually life in the Milky Way. I think this goes way beyond geology. I think there's so many processes that contribute to these little sampling, sets in these objects of chemistry and galactic evolution. You can think even of, panspermia theories where these objects are basically, building up certain type of compounds during their journeys, and then they are, pollinating the rest of the newly forming planetary systems. And so there is a tremendous amount of insight that stands in front of us, and we just need to tackle it really with all possibilities of observations and simulations, and chemistry and astrophysics go hand in hand here. And I think we will find big surprises when we have the first, let's say, object that comes really close to Earth, and where we can get extremely high resolution, high signal to noise spectra, and potentially a sample return. I mean, think about placing a probe basically on each of those interstellar objects that are coming relatively close to these comet interceptor constellation satellites, and you hitchhike through the galaxy, right? So you look how the object in situ evolves, right? And the sooner we can do this, I think the smarter we will get how unique we are in the Milky Way.
Now, you mentioned phosphorus earlier, which is an open question regarding the galaxy and life, because you need phosphorus for life. But there is some evidence from other papers over the years that it might be spotty. The abundances of phosphorus in the Milky Way might be a little bit spotty, which is probably a showstopper for abiogenesis if you don't have enough phosphorus. And we have phosphorus problems here on Earth. The availability that. Now, what abilities do we have to study the abundances of phosphorus in interstellar objects?
I mean, first of all, we have to, look at getting high enough signal to noise, high resolution spectroscopy to actually isolate individual transitions in these spectra. They will be weak. Exotic elements are having, of course, an abundance that is tremendously smaller and lower than, for instance, the iron peak elements and the light elements, carbon, nitrogen, oxygen. But it's not impossible. I think the more carefully we look, the better measurements we will get. And you're absolutely right. There is a dearth, there is flocculence in the chemistry of phosphorus in the Milky Way, and also in other galaxies. We will have to see. And I mean, this is an open book that we start to write right now. So I'm letting the universe come towards us and tell us the story about how the currency of life, right, phosphorus, is imprinted into the chemical evolution of spiral galaxies and other galaxies for that matter.
And in terms of how we have detected phosphorus, so even in solar system comets or other comets, phosphorus is usually detected in a handful of bright comets because it requires very extreme heating. And most common detection happen in like sun grazing comets where the dust vaporizes. So for example, there was a comet Lovejoy from 2014 where the PN emission is detected. So most of the challenges are the sublimation temperature. So nickel, for example, sublimates at 200 Kelvin while iron is 220. But phosphorus are locked in refractory phosphides, which can sublimate at 1200 to 1500 kelvins. And thus observing them can be difficult. And also, if we were to observe these weak features, we would observe them in like UV lines, which are difficult to observe from ground itself. So using of a UV space observatory, for example, a UVIT telescope would help us in detection of these phosphate compounds.
Non-gravitational acceleration. Now, this object is starting to show that, and we're starting to see velocity changes with it. And we also have the effect of the sun, which I believe is slowing it down compared to its velocity when we first detected it. Now, what is the difference? And is it correlating with the profile of what the object is doing in regards to outgassing, which it seems to be doing much more heavily as expected now that it's just past perihelion? Give us a profile of the non-gravitational acceleration.
So to explain briefly, comets exhibit non-gravitational acceleration, which are sort of rocket booster effects. When a material is basically ejected preferentially from one side of the nucleus, it imparts a net force that alters the orbit slightly. And this is a documented phenomenon in hundreds of solar system comets. So for 3I Atlas, the observed non-gravitational acceleration was approximately 10 to the negative 7 meters per second, which can be explained by very modest mass loss, which is basically about 0.7% per day, assuming some ejection velocities. The key point is that acceleration does not need to persist for extended periods. If acceleration occurred during a brief active period lasting hours or day, when the comet was most active near perihelion, the total mass loss would be a small fraction of the nucleus mass. And the comet has been observed to go, for example, dramatic brightening, consistent with the increased outgassing activity. And this would, for example, I think it was recently studied where they documented a brightening increase of R to the 7.5, sort of similar to the production rate ratio that we have for nickel, and the comet becoming blue as gas emission dominates. This provides the mechanism for acceleration. So increased outgassing activity with preferential from one side of the nucleus, with inclusion of geometry and things, for example, rotation, can lead to these non-gravitational acceleration. But the paper demonstrates that the CO and CO2 composition is 1% of the surface area. And basically, the data of composition of C, CO, all these gases can be used to reproduce both the magnitude and direction of the observed acceleration with physically plausible parameters. So we don't need to invoke any exotic physics or explanation to explain these non-gravitational accelerations.
These outgassing events, right? They elevate the dust into these beautiful tails, and at the moment, our viewing geometry is unfortunately very unfavorable for us to see this tail morphology and the structure of, well, first there are different tails, right? There's a gas tail, there's an ionic tail, and there's a dust tail, and so all of the morphology, right, with the expectation of the radiation pressure, which pushes, right, the dust tail, that structures the dust tail, and the solar wind pressure, which ionizes basically the gas molecules and carries the ionic tail away, and you have the observed morphologies. We know from space weather studies, right? So there are many different satellites around the sun that monitor basically the activity of the particle flux out from the surface of the sun and how it impacts our planetary environment. And so just recently we had this wonderful solar storm, and I think in North America there was quite a spectacle in the sky over the past few nights. So these wave fronts of particles arrive at the comet and basically structure the ionization and the tail morphology to a certain degree. But it's really like for the dust, it's the radiation pressure that carries and structures these tails. And so this is perfectly consistent with what we expect, what we calculate. And we will see as the comet basically moves towards perigee, the closest point to Earth, on December 19th, right? We will get a slightly different perspective on the tail morphology, and we will be able to take spectra and study actually the types of materials, so the gas component and the reflectance, and hopefully with a specific technique that we have in mind, we will be able to constrain the size of the nucleus a little bit better than what we will be able to do or what we were able to do so far from the HST images that we took in August, I believe.
Are you expecting it to be relatively small? In other words, there have been some estimates saying, well, this thing could be enormous, which means that it's very unlikely we would see that this quickly. Are you expecting the constraints of the size of the nucleus to reduce?
We hope so. I mean, we will have a better vantage point, right? The distance to us will be minimized at perigee. So from ground-based observatories, we will try to push the resolution limit to a few kilometers, maybe arriving at 2 kilometers. This will be a very solid upper limit. We don't know exactly the size of the object because we just simply don't have the data to resolve it, right? So far, the best angular resolution image is that one from HST. The high-rise camera will probably compete with this to a certain degree, although it's still, let's see. But that gives us a very solid upper limit of 5.6 kilometer diameter for 3I Atlas. The lower limit is related to gas physics, the volume of gas, what types of volatiles are assumed on the surface and subsurface, and also with the thermal modeling at the time when the image was taken, right? So there is a solid, also I would say, lower limit of a few hundred meters of diameter. So anywhere in between there, right, there is the truth, and makes absolutely no sense to speculate now based on outgassing morphologies, tails, misunderstanding of astrophysics, that the object is ginormous beyond 20 kilometers. That has absolutely no footing in reality and scientific endeavors.
Well, it's worth noting that it's bathed in a coma. And seeing something that is living inside of a large, thick cloud and figuring out how big it is hard. That's very difficult.
It is a tough endeavor. I mean, you have to peer through the dust and the gas, right? And so you have to catch it also in a state where it's relatively calm, right? Where you can look down onto the nucleus. And so, you want to look at this probably in the infrared. And so there are certain ways to maybe get to this in a slightly more accurate way.
Now, looking at it in infrared, that seems to be right up the alley of the James Webb telescope, right?
That's right. Yes. So James Webb, I think, will have a very good opportunity to constrain the upper limit, in a very orthogonal way to other instrumentation. Hubble will be looking at this also from a slightly closer perspective, as will James Webb in a certain way. But we also on the ground will have the opportunity of measure the size, with certain techniques that are, and they all need to basically paint a consistent picture, right? So if there is something off, well, then this, will be a good trigger for the thought. But all the different orthogonal lines of evidence need to paint a consistent picture, and then we will get closer to the true size of this object, which is really important to know, right? Because we really want to basically set sort of the initial mass spectrum and size spectrum of these objects, and then you can go more into details about density and chemical composition. And so size really informs a lot of the properties of these types of objects.
Now, radio emissions, and this is really, really new, where you're seeing absorption lines that give you a little bit more of an insight on the chemistry of the object. What more can the radio telescopes do? And like with this hydroxyl detection, what more can be done in the radio regime
Well, I mean, you can look, depends how you define radio, right? So you can go to like short wavelength radio, which moves then to submillimeter, and there you can look at this object with telescopes like ALMA. We have a program running that observes 3I Atlas. In fact, we've been basically tracking, I can say this now here, we've been tracking 3I Atlas throughout perihelion, and it was where it was supposed to be, and everything was fine. It was a comet all the way through perihelion. It shows really interesting outgassing patterns. So there is something to be said about the gas dynamics immediately in the high density part of the coma, and that is being analyzed right now. So we have a program going on with colleagues at the institute here, and I think we're going to have very, very interesting results soon to be put on archive. So yeah, stay tuned for that. I don't want to give out too much yet, but it's everything is consistent. It looks very dynamic, very interesting, and it makes perfect sense astrophysically.
Now, does it appear, based on what you've seen so far, that this is the first close interaction this object has ever had with the star system? In other words, depletion. Or do you see any evidence that this thing might have, and I can cite solar system comets, because you get a new one coming in and you can have absolutely spectacular tail. And if it comes close to Earth, you've got a great comet, which we've had in the past. The best one I ever saw was Hale-Bopp, but you don't, does it look like this object has danced with other stars before?
That's a beautiful image. I like that. Dancing with the stars, yes. So it seems like 3I Atlas came in already puffing, right? And so that speaks to some form of early onset of outgassing modulo trigger modulo environmental interaction. And so one sort of speculation that we were floating around in our team is what happens if these objects really go through the heliosphere, the helio sheet. And that really depends on the direction where they're coming from, right? So there, the enhanced environmental conditions and electron densities and by the accumulation of the turbulence and the radiation environment in general, I think might lead to some form of mechanism. We are really not experts, so we leave this to the people who model these effects. Magnetohydrodynamicists who really look at how comet icy silicate carbonaceous surfaces react to that kind of environment. But we can see that this might actually be to a certain degree contributing to a, let's say, pre-puffing of the coma. How now the pre-processing has worked in interstellar space, that of course is degenerate with the formation chemistry, how it was actually put into the Milky Way in the first place, right? So I think that requires really much more study and much more diversity in different interstellar objects, and basically building up this library of types of surface chemistries at different heliocentric distances and how they react to our local environment. And that is not only the radiation of the sun, but also the bombardment by solar activity. So it depends really when you look at these objects, at what distance, at what cycle of the sun we encounter them in our solar system. So all of this is in some ways a degenerate game and requires much more data to really nail it precisely down.
Yes, but with Vera Rubin, we're going to get much more data. We're going to get a big sample. Now, what do you expect of the future for interstellar objects? Once Vera Rubin is in full operation, and I know that it actually they didn't know it at the time, but they accidentally caught 3I Atlas very early on, and they look back at their test data and there it was.
Yeah.
But what do you expect? How many interstellar objects in general, asteroids, comets, all of that, how many do you expect per year to be detected and studyable? And what's this going to look like in 3 years to study these objects? Are we going to know a lot more from a much larger sample, hopefully?
Yeah, I really strongly hope so, that we're gonna very quickly discover 4i, 5i, and so on. I mean, Rubin demonstrated its power of really like harvesting the sky for these moving objects. So at the moment, the best estimates I think that we have is somewhere around one to a few per year. And this might change, right? So we're basing the statistics on these very few interstellar objects, confirmed interstellar objects that we have, which are 3. And so, be my guest and do, statistics with three sample size inference, right? So there is really anything above and beyond. There is a limit, of course, to the overall density of these objects in terms of mass density, right? So you would not expect too many of those, especially too many heavy of those to be floating around, since we would basically be limited in certain aspects in dynamical evolution of the planetary system, where the planets would be basically bombarded or deviated or swung around, or the moons would be destroyed. And so there is an upper limit on the density of that. But from what we observe of the mass around young stars forming planetary systems, protoplanetary disk, it's about an Earth mass per star that goes basically into interstellar space. And so that just gets distributed in the Milky Way. And then the more sensitive the telescopes are that we have, the better selection functions in the sky we construct with our surveys. And so Vera Rubin is one step forward. I mean, we can think about putting another Vera Rubin in the northern hemisphere, and then we would increase our detectability chances for these objects, and we will just harvest the sky, right? So Rubin detected in a few nights, about 2,000 new asteroids. And I mean, this speaks for itself, right? So it's a very powerful facility, and we're really looking forward to the data, hopefully next year, and that will be streaming down into our hard drives and giving us excitement here for following up these objects spectroscopically and with other facilities as well.
Yeah, near-Earth asteroids and mapping them and potentially having to deflect them.
That's right.
Is something that I'm very hopeful that Vera Rubin will get a lot of data on.
Yeah. And
even small objects, things that aren't... They're dangerous enough to damage buildings in Russia type things with like the Chelyabinsk meteorite. Well, they can see that. And I'm extremely excited for it. But you're right, we need one in the Northern Hemisphere.
Yeah.
But what do you think, and the other thing too, is, they talk about that 10-year survey regarding Vera Rubin, but the telescope's not going to go away after that. It'll still be there for much further work. What do you think we can do, though, as far as interstellar objects? And we were talking about sample returns. What types of spacecraft, if I gave you unlimited money and say, design a mission to be able to go out and get us samples and return them, and, go on the model of the Japanese with JAXA, and, where they went to Hayabusa and all that and did sample return missions. What can we do as far as spacecraft, the ideal spacecraft mission to get samples from an interstellar object from your point of view, if I gave you unlimited money?
If I have unlimited money, I would probably design, a multi-satellite, these microsatellite missions that park, probably dozens to hundreds of these small satellites in sort of inclined solar orbits and park them there simply and have a limited amount of thrust on these little entities and then just simply wait, right? So there are many interesting, it doesn't have to be even an interstellar object, right? It can also be an interceptor for, let's say, centaurs or really weird Oort cloud comets that come through, and those are equally interesting. And so I think having sample possibilities premeditatedly parked in these orbits that are energetically not too expensive to populate and have a very good chance, of course, this would have to be modeled with what we expect to come in from what direction and in what orbit angular momentum configuration you want to have these satellites floating. And this is completely beyond our pay grade, but I'm pretty sure it's easy to figure out for the experts, and I think that would be an amazing mission to do. I mean, there is the Comet Interceptor mission concept that will be built. I vaguely I'm aware that there's, I think it's ESA, right, that is building this and probably launching very soon. And so this will be like a test case, and I'm pretty sure we can miniaturize these satellites so we can send probably dozens or hundreds up there and just simply wait.
I think one of the interesting things that astronomers can contribute to now, until they wait for the unlimited money, is where to put these comets or where to look for it. So, for example, LSST is going to scan this entire southern sky, but one of the questions we can ask, let's say we put in 3 JWST, where should we look for these comets? Where should they be coming from? Where should we throw this net of observation so we can catch these objects? And 3i Atlas is very unique in that aspect, I think, because our solar system is, for example, moving in the general direction. We are in our galaxy, we have the ecliptic, and our solar system is relatively flat. So unlike previous objects like Oumuamua and Borisov, which came from above us, basically we crashed into them instead of they coming into us, because our solar system is basically moving through the disk, and this was like a head-on collision. 3i Atlas came from a less crowded ancient region, so which is called the thick disk. So that means 3i Atlas is not something we should expect to see as much with LSST. So if we want to plan space observations, we might have to set up to observe different regions of the galactic disk, and that's something that is also interesting when we have many comets to see distribution function. So do comets that come mostly from the thick disk, do they have certain particular properties, or compared to comets that are through the moving disk of the ecliptic plane or head-on collision? And that can give us sort of another tracer of a distribution of what kind of comets we should expect from what part of the sky. And I mean, you can go nuts with this theory in the future where you have thousands of data. You can look in particular directions to get sort of a heat map of what kind of objects you can expect to come from where.
I mean, at some point you also will have a very good idea, when we're talking about like thousands of interstellar objects at some point, right? Where you can build up basically, and we talked about this in the beginning, about this initial chemistry, right? The nucleosynthetic patterns of enrichment of the galactic environment. And so if you go into the different morphological components of the Milky Way, right? So we have the thin disk, we have the thick disk, where 3i Atlas is from apparently. The primordial history, right, touches essentially the hierarchical building scenario of galaxies, right? And so you might actually go at some point and find an object that is genuinely intergalactic, right? That comes maybe from, whatever stream has been absorbed by the Milky Way billions of years ago, and that comes with its own stellar population, and the stellar population comes with their own, planetary system population and exocomets and interstellar objects. And so we might actually be even more surprised that we are surprised right now by, the properties of 3i Atlas. I think, we just cracked just a little bit open the door to this amazing new field of galactic archaeology, right? And in terms of star formation, chemical enrichment, and planetary system physics, astrophysics.
Well, as a thick disk object, which it appears to be, which is sort of circumstantial evidence linking it to that, but it appears to be that, and that's an older population of stars. How early can we get? In other words, as we look at further interstellar objects, can we see something that is 10 billion years old, or something like that, that starts getting really depleted of things like nickel, where you just don't see as much? Is it possible for us, and how likely is it, to see a fossil from very, very early in the Milky Way's history, just when it could form, an object like this, form planets from that period? Could we see that? I mean, could we see a fossil from that period, or would they just simply be very rare by nature, or what is the profile there?
I mean, could we see them? Yes. Are they very rare? Yes. Right. So that depends really on the mass fraction of the stellar population that makes up, in our case, the thick disk versus, other components like the thin disk and the halo. And so the halo, right, is not very dense in terms of stellar mass. The thick disk is also not very prominent in terms of stellar mass. I mean, it's a fair fraction, but it's not, a dominant component. These components are really early forming. They have been basically disturbed gravitationally by the merging events of the Milky Way and have been sort of dynamically heated up by the inflow of mass into the early Milky Way. And so, yeah, it's absolutely perfectly reasonable to expect a fair fraction that will scale with the mass fraction of the corresponding stellar mass that is being locked up in this morphological components of the Milky Way. So we expect many, many more thick disk objects of that kind. But there will also be a few percent to 10% to maybe a little bit more. Depends how they have formed, how they have lost the outskirts of their protoplanetary disks. And yeah, it remains to be seen.
The elephant in the room, which for our solar system is Jupiter, and capturing interstellar objects. And I know that there are at least two candidates I'm aware of objects in the star system already that may have originated as interstellar, which means they'd be fairly easy to study, although being in the star system like that for that long probably changes them. What are the prospects there? Do you think that we have captured interstellar objects that we'll look at isotope ratios of as we explore the asteroids and see that, yeah, this isn't from here? And how does that play in the future in understanding interstellar objects based on what we've captured?
Well, I think there are two sides of this story that are really challenging. So you want to have sort of pristine material that basically comes in unprocessed into our solar system. And that means you will see these objects very far away. There will be very little light reflected off them. And so you will encounter them in the outskirts. And there, the activity will also not be, significantly higher than typical Jupiter family comets or even Oort cloud comets. So catching those objects really early on in their first encounter of basically the inner solar system is really crucial. And there might be earlier caught interstellar candidates floating around in the solar system, but they will have processed surfaces, right? They will have already altered chemistry, and we will have to put them in a slightly different pocket. They will be interesting on their own, right? So they will probably exhibit isotopic ratios, like you mentioned, in a very particular way, and have sort of their birth isotopic chemistry locked in and demonstrate us hints of their origins. But really the first infall interstellar objects, I think this is what we really, really want to study. Because then you really know that this is a pristine laboratory and you're looking at something genuinely unprocessed by our stellar environment around the sun. So we are actually, we're looking, we have another program going on with a high resolution spectrograph on VLT, and we're looking at the isotopic ratios, in particular the carbon and nitrogen isotopic ratios on 3I Atlas. And so far, it looks interesting again. So there are some really good measurements so far that we obtained. Again, I don't want to jump the gun here and spit out some results that will change, but there is some leverage on, in particular, the carbon 12 to carbon 13 and then nitrogen 14 to 15 ratio that place the birth location of this object in a certain context in age and in the galactocentric distance. There are certain models that people run, so population synthesis models that calculate how individual elements are enriched by different types of stellar evolutionary epochs, massive stars, fast rotating stars, novae, and so on. and where individual isotopes predominantly come from, and that basically scales or converts into a scaling relation of these isotope ratios in the Milky Way disk, and they get pretty much preserved, right? So as the comet travels and ages, we know how to infer, these ratios, and that gives us hints for where these objects might be coming from.
There is so much I wish we could know, and we're not going to be able to, but there's so much, because it's like, your immediate question when you think about this is, what ejected it? Was it an encounter with another star? Was it an exoplanet? What ejected it? And we can't ever know, nor can we ever know what star system it was from originally. And that I think is the maddening aspect of interstellar objects and studying them. But it certainly, again, is a good sample return. Now, my last question for you is the other elephant in the room. And I have to be clear that I believe this to be a comet, and I think early on it was clear that it was. But there are those that are suggesting and saying that, well, maybe it's not. Maybe it's artificial. Maybe it's a piece of alien technology. And my initial reaction was, no, it's not weird enough for that. It isn't strange enough. But I wanted to get both of your views on this and let you guys address it.
Yeah, so that's a big elephant in the room. As far as we can tell, with the data that we have and that we are aware of, there is absolutely nothing that indicates anomalous behavior in the sense that there is some weird non-astrophysically understood component of the data that we observed. Of course, that does not mean, right, that in the future there might be something even weirder coming along that we might need to reevaluate, and we might expand our horizons, but empirically, right? So based on evidence. Science is an activity that is based on evidence, and then you can make up your beliefs based on evidence. It's not putting out beliefs and then wait until they are disproven. Okay, this is not how science works. This is really important to understand. We really write proposals. We think about the implications of observing runs of data that other people have taken, of our data that we have taken, and we take steps forward in widening our horizon of understanding and the implications, and we believe us. We have been looking for weird stuff in the spectra. Okay, we have been looking for, whatever, hydrazine and stuff like that. And so there is absolutely no indication that this is rocket-propelled stuff that is floating through the solar system. There is absolutely no indication other than this is a very interesting natural comet that has been sent to us by the Milky Way gravitational potential and the sun, of course, that we need to study. And we are keeping an open mind, and I said already, right? So the calmer you observe the universe, the more you reduce the noise of your observations. You don't have to go out and throw out speculations. The universe will talk to you, right? You just need to observe. And then the interpretation falls almost, by itself on the table, and you just need to grab it and interpret it and basically make up a self-consistent astrophysical model for this. If there is any indication, and I promise you, if there is any indication, we will be the first ones, right, to blow the whistle and say, ooh, there is some weird nitric oxide stuff that is floating around 3i Atlas. But it didn't happen so far. And so it doesn't make any sense to disturb the public, frankly, and scare the people that this might be an alien spacecraft and it will, launch probes that will invade the planets and scan our intelligence. And there's absolutely no foundation for this, right? This object is interesting for very different and more beautiful reasons than this sensationalism that is being spewed out into the public at this point. Astrophysics is a beautiful activity, right? Science is a beautiful activity, if you base it on evidence, right? You have to work hard. It's not just doing a few calculations and then putting them on a blog post. Those are adorable attempts to put something out there into the public, but they are misguided and they are dangerous. And I hope this will change, and I hope the public will realize how wonderful and beautiful this type of astrophysics that just opened up to us is actually, and what we can learn from further investigating scientifically, not based on sensationalism and speculations, but on real astrophysical evidence. There's so much more to understand, and I hope this arrives at some point in people's minds how wonderful science can be actually.
I mean, I could speak from my experience of how we, for example, detected the nickel when we were observing the data for the first time. We observed these specific lines that were increasing. And for example, nickel lines are in a very bluer part of the spectrum. And the more bluer there is, the more noise there is. And usually astronomers, for example, if it's very close to the instrument's response function, which is or to the bluer spectrum, you can ignore it as noise. But when we saw over multiple time series, we saw these specific lines that were increasing. Now, the reason I'm talking about this is how maybe this is not an advice for general public, but this is how maybe we think of anomalies. So when we saw this, was like, okay, these could be lines, and let's investigate and see what previous comets or have been observed. And then we found that these are actually nickel lines which have been observed. So similar anomalies that have been spreading in the public were also observed by us, and when we got more data, we were able to explain them with physical explanations. So maybe I could highlight some of the anomalies. For example, one was the low inclination to ecliptic, which is sort of a selection effect because objects with low inclination have longer visibility windows, and that's why I have higher discovery probability. We also observed that the comet was coming to very close to planetary approaches, which was like 0.2 AU to Mars and 0.36. But AU is a distance unit astronomers use, which is millions to tens of millions of kilometers, which is not very unusual in comet dynamics. Then we saw perihelion during solar conjunction, which is a pure geometry with no physical significance. I mean, having the comet itself travel for 10 billions of years, it's very low probable to have encountered a system, let alone a system that possesses life. So if we were the comets, I think comets should be more surprised to encounter us than we should be surprised to encounter the comet. And there were more anomalies like sunward plume, which was initially mischaracterized, which was actually a well understood phenomenon which have been observed in distant comets, for example, C 2014 UN 271, which is caused by preferential sunlit hemisphere outgassing. There's the high Ne and nickel to iron ratio that we observed. There's non-gravitational acceleration, which we were able to explain. There's the brightness in spectroscopy. The apparent size, which was initially overestimated, is because of the coma brightness, because it was much bright. And as you can see with JWST and future observations, we are going to constrain the nucleus size more and more. And then there's statistical philosophies, for example, choosing a specific trajectory elements after seeing the orbit inflates the apparent significance. And so meaningfully attaching hypothesis to something based on you have already observed, or which is what no p-value, I think is what was mentioned, can be meaningfully attached to a configuration you've selected after observing. The whole point of science is to make hypotheses and see if the hypothesis is proven right or wrong. So yeah, I mean, these are some of the famous anomalies that I saw that were being discussed, and we were able to explain all of them through just simple astrophysics and first principles. And that's what science is, to be able to explain it through the first principles, since science only advances, as Thomas said, when you can make new hypotheses which can be proved or disproved scientifically. And bringing up things like alien is not really a hypothesis. It's just putting a statement which we can't really prove or disprove. So, yeah.
If I may add something really important, I think that needs to be said here is that science is a group activity. It's not a commentator job looking at papers on archive and then coming up with weird inferences about the nature of, 3i Atlas or any other mechanism around it. Before you do that, you talk to the experts, right? This is what we do. We take data, and I want to point out the other really important members of our group, Juan Pablo Carvajal and Baltasar Luco, who are not with us today, but they contributed an enormous deal to taking the data, reducing the data, analyzing the data. And we all four of us, we talk to experts in the field. We are, we're coming from a different field. We have our large language models of astrophysics in our heads, and we are using this, right, to our advantage. We interpret the data together with the experts that have worked in this field for decades, and we ask questions. Does that make sense? Is this consistent with what you would expect? We see this result. We have modeled this in this way. Is that consistent with your experience? And this is how you get into a consensus. And we learn from them, and they also learned from us, right? Because we came sort of orthogonally also into the comet sphere, and we didn't know everything. And we, both teams and actually many members of our larger team, have been learning a great deal from each other during this time. And so it's really important to get down to earth, reduce the hubris, and get basically a scientific consensus into the world that makes sense of reality based on fundamental evidence, not on speculation.
I think it's important to hammer home something in that when you're dealing with an object that was purposely built by an alien civilization, it is going to be so much stranger and probably more obvious, if you can see it, than this object is. In other words, if you saw an object cooking through that was throwing off very short-lived isotopes of radioactive elements that it shouldn't be producing at all, things that it just shouldn't be doing, or technetium or something like that, this could get so much stranger with an alien spacecraft that it's not even funny. And this didn't even get really into that arena, I don't think. But it could get so much stranger. Do you think the study of interstellar objects, and I get to ask my crazy question, do you think that is a fruitful area for SETI to start looking at the composition of interstellar objects and see if someone is sending a message in a physical object producing materials that it has no business doing so in nature?
I mean, fact is, we have been doing this, right? There is the Pioneer probes, there are the Voyager probes, there is the New Horizon probe, and they will leave the solar system, right? So they are sort of our artifacts, compendiums sort of our technological prowess of the civilization that we call Homo sapiens. And they will be floating around there. And so there is no reason to believe that if, and that's a big if, right, there are similarly technologically advanced civilizations in the depth of space-time in our Milky Way, that these objects might be floating around. Of course. But again, right, you need evidence. And I agree with you that I think if we will encounter something, like a dead space probe, the absolute ridiculous exotic measurements will accumulate very, very quickly. And so we will be steered very quickly, I think, into the direction of extremely unusual, exotic, let's look deeper situations than we have basically in front of us in the form of 3i Atlas. I mean, 3i Atlas is, why would you, camouflage yourself with a coma in a dust, astrophysically self-consistent environment to, I don't know, check out the solar system, I mean, that's a massive waste of energy, if you ask me.
If I could add, because you asked, as you say, I also like to dabble in the crazy theories. And from an anthropogenic perspective, let's say we had the unlimited funding, what I would do is we would have space probes that we would put on this comet, because this is sort of a easy lift taking you to other systems, and it would be a perfect thing for humanity to put a probe that is putting specific radio signals or something. So when 3I Atlas goes out of our system and into interstellar space, we would be able to broadcast our presence. And so with the two options of if alien species were trying to reach us, they would have a very fundamental and much better understanding of interstellar objects. And so they would, as Thomas said, if they wanted to communicate, they would make objects that are free of this coma and astrophysical noise. They would be very direct, so that another intelligent species like us would be able to tell directly that this is not natural, this is something artificial. And if their goal was to, I don't know, stay hidden and be like a spy, then I think they would do such a good job where we won't be able to even detect this object in the first place.
Well, I don't think they would disguise themselves as a comet that gets our attention.
Yes.
I think they would either be, as you say, invisible completely.
Yeah.
You know, make your probe the size of a baseball. We'll never find it.
There is this argument of this black swan event, right? That is being sort of sermoned upon us. And in the case of a black swan event, do we really think that we will be able to defend ourselves against, such an amazingly more advanced civilization that tries to visit us? So it's an absolutely ridiculous argument to pull, and in this case. So if we find someone who wants to invade us, it's game over, and there's good luck, run for the hills. That's my advice. And if it's someone benevolent or something benevolent, well, then we take full advantage of our encounter, and hopefully we will grow together as a super species.
A super species, that's an interesting idea. Unfortunately, with AI in the mix, I don't know what's gonna. we might not be the super species. The AI might be that we produce. Now, is it possible that since we have so many interstellar objects apparently coming through, and you start sticking probes to them and use them as your way to explore the galaxy, do you see that as a possibility in the far future where we could sit there and just start making generic probes that are sending data home from the interstellar medium? I guess it's probably relatively unlikely we'd get to another star system, and that gets really uncertain. But is there a utility to at least studying the interstellar medium, because these things can move fast, to stick probes to them and explore the galaxy that way?
Sure, absolutely. I mean, that is a viable, proposal that you should probably pitch to a space agency to park, some of really radioisotope powered, I don't know, several decade lifetime probes that park our, I don't know, Wikipedia on top of this thing, and
like the golden record.
Like the golden record, exactly, and have some form of very basic low energy consumption measurement facility sitting on top, and then just explore.
I think it's a great idea, but the issue with that would be receiving the signal. So, for example, to give a context, unfortunately or fortunately, space is very, very huge. And for example, when the comet, which entered our solar system, the very outer edges, which is called the Oort cloud, which can span up to 100,000 AU, it entered like 8,008 years ago, 8,800 something years ago. So the goal would be we could park them, but by the time we get data from the ISM, it would take a long time. So that would be the only issue with that.
It depends how long you expect us to be around, given that AI is going to take over soon.
Yes. The AI will solve it for us. It'll come up with a plan, and we'll just let it do the exploration and tell us what it finds. Now, how easy is it to use AI in this context? What do you use? What's that look like that you're, as you study this object, what sort of machine learning and things like that are you using to characterize it, or if any?
Well, I mean, we've been using machine learning algorithms pretty much for the last, decades. So there is, of course, different types of machine learning and artificial intelligence algorithms out there that you can use. We've been doing, a lot of Monte Carlo inference, a lot of little bit of Bayesian inference, so that is coming up in the papers, and so these tools are, commonly used by astronomers. I mean, this is nothing new to us in a sense. Concerning large language models, what typically we use it for is literature search. So we discover publications. So it's an easy way to find really pinpoint key publications in the past that we can, download, read, and the advancement of our understanding has been really boosted by the availability of large language models. Just simply using this as a, I don't know, as a companion along the way of scouring libraries of publications, scientific papers out there.
Yeah, that's one thing I do not envy people authoring papers, scientists authoring papers, is finding out about everything you need to cite and doing it that way. And it must have been much harder 10 years ago than it is now. But then you get, accused of, hey, you ignored my paper from 1988 or something like that. And that must be absolutely maddening to have to deal with. All right, gentlemen, I'm very excited about this object because, again, it's a fossil giving us information about the history of the Milky Way, and I hope we find even older ones so that we can compare, and just see what are the differences. And also, where in the galaxy did it come from? And maybe we'll see something very strange that isn't from the thick disk or is from the galactic center or something like that. I don't know how easy that is to eject an object, but it's very exciting and a budding field. And I wish you both good luck in studying these objects and getting even more data from the Vera Rubin telescope.
Thanks so much. Yeah, we're really excited about the future of this.
Thank you so much.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.